Alright, so we're talking about something new today. We've already talked about velocity. Which was simply the change in our displacement over a time period. Now we're going to talk about acceleration. And acceleration is a pretty basic concept. It means change in velocity over a period of time. And that means that acceleration can be slowing down, speeding up, and actually changing direction as well, since velocity also involves a direction. So what is it? Change in velocity. How are you changing with speed? Are you speeding up? Are you slowing down? Are you changing direction? These are the three pieces, well, one of the three things that needs to happen for acceleration to be taking place. And acceleration really is, our body feels acceleration. We feel when we speed up in an object, like a car or bike or whatever. We feel when we slow down in an object. And we also feel when we change directions. This is what makes amusement park rides so fun, acceleration, because it's the change in speed or velocity that makes it fun. If it just went at a constant rate, where there isn't acceleration, it wouldn't be much of a ride. So acceleration is something that we all feel, whether it's speeding up, slowing down, or changing direction. It is a vector quantity, it's not scalar. So whenever we give direction, we need to give two things. We need to give not only the size of the acceleration, but also we need a direction. Is it going in a positive direction? Is it going in a negative direction? These are things that we need to be able to figure out if we're solving for acceleration. If an object's velocity is increasing, acceleration is in the same direction as the object's velocity. So if an object is traveling in that direction, let's say a positive direction, and it's speeding up, then we say that the acceleration is also that way. We haven't really talked about vectors yet, but vectors are simply arrows that represent quantities in physics. It can be up, down, left, right. So this arrow here is supposed to represent an object moving to the right, and if it's speeding up, the acceleration would be to the right as well. But if the object's traveling this way and slowing down, then the acceleration is set to go in the opposite direction. So here, if the object is moving in a positive direction, the acceleration would be negative. Up here, if the object is going faster in a positive direction, the acceleration would be positive as well. So, previous slide, really the same thing, just a lot fancier graphics. If we have an object with its velocity going to the right, then the acceleration, well, let's check that. If we have an object moving to the right and its velocity is getting bigger, it's increasing, it's going faster, then the acceleration is going to be to the right. Acceleration is going to be in the same way. If the object's slowing down, velocity is getting slower, then the acceleration is going to be the opposite way. So if the car is moving that way, like let's say it's moving just away it's moving to the right, but it's coming to a stop sign, then we would say the acceleration is this way. And let's say that it's leaving the stop sign up here, so it's moving to the right, and it's speeding up, so its acceleration would be to the right. Alright, so pause it for a second and answer these questions. Alright, a passenger train is traveling on a straight track with a negative velocity. It's very good, I've said this before, always try and write drawings when you're doing these problems. It's got a negative velocity, okay, so it's going to the left with a negative velocity and a positive acceleration. So this is velocity, and if it's got a positive acceleration, that means acceleration is this way. Now we just said earlier that if the object is slowing down, that its acceleration will be opposite its motion. So what is this object doing? Well, I see velocity pointing to the left. I see acceleration pointing to the right. The velocity of this train is decreasing. It's getting slower because they're opposite directions. The second one, Kyle is riding his bike and slows down as he approaches hikers on a trail. So he's slowing down, his velocity is getting slower. Explain how his acceleration can be in a positive direction even though his speed is decreasing. Well, if he is traveling to the left and he's slowing down, we would call that a negative direction. If he's slowing down, which does acceleration have to be? Has to be to the right, and of course to the right is positive, so the acceleration is positive while the velocity was negative. So that's how his acceleration can be positive, because if he is going in a negative direction and slowing down, his acceleration has to be the opposite direction. So what's the opposite of a negative direction? Positive direction. Alright, the formula for average acceleration is pretty straightforward. It might have lost a little bit of graphics in the conversion to this program. VF minus VI over T. So VF stands for final velocity, VI stands for initial velocity. So you can have a negative number up top, and then T of course is time. So the change in the velocity over a period of time is what we call acceleration. So you will find this in your formula sheet. Alright, remember velocity was just a change in displacement over time. I think we said x sub f minus x sub I over time. Alright. And what did we end up calling xf minus xi? We just said that was the delta x, the change in displacement over time. Well, you can see now we're incorporating velocity into the top. So when you see delta v, again, that means change in velocity. And to find delta v, you would simply subtract vf minus vi. So let's take a look at this question up here. I want you to predict what the speed for the car is going to be after 3 seconds. Take a moment and decide. Alright, so after 1 second it's going 15 miles per hour. After 2 seconds it's increased to 30, so it looks to me like it's increased by 15 each second. So at the end, our speed, our velocity, excuse me, would be 45 miles per hour. So how would we describe that if we were going to describe its acceleration? Well, every second, its speed is increasing by 15 meters per second. Every second, it's increasing by 15 meters per second. So you get 15 meters per second, which looks kind of weird. So instead of writing it that way, we typically see it written 15 meters per second squared. And the squared, of course, comes from something we'll look at later. But that's how you end up getting the unit for acceleration. So here's your meter per second over second. If we split that into two, it's a meter over a second times 1 over a second. You think of this like a big fraction. And of course, a second times a second is a second squared. So it's how many millimeters per second an object's velocity increases every second. It's the change in the velocity over a period of time. And it's very common for students to forget to put that squared sign on there. Meters per second squared. It also can have other units. Miles per hour squared is an acceptable unit for acceleration, not a very common one. Miles per minute per second would be an acceptable unit for acceleration. It just needs to be a velocity unit per a time unit. In this case, you wouldn't be able to have a squared because it's not the same time unit, but you could convert it if you wanted to. So just to sum up our concept of acceleration, we have at the first column, if an object is moving in a positive direction and its acceleration is also in a positive direction, they're going the same way, then that object must be speeding up. If an object is moving in a negative direction and acceleration is also in a negative direction, that object is also speeding up. If an object is traveling in a positive direction, but its acceleration is in the opposite direction, in this case negative, we would say that object is slowing down. If an object is traveling in a negative direction, but its acceleration is going the opposite way, again, it's slowing down because they're in opposite directions. If an object is traveling in either a positive or negative direction, but it's not accelerating at all, in other words, it's not speeding up, it's not slowing down, it's not changing direction, then we say it's just traveling at a constant velocity and there is no acceleration. If an object is traveling, if it's starting at 0, its initial speed is 0, and its acceleration is either positive or negative, then we say that it's speeding up from rest. And of course, last one, if there is no initial velocity, then there is no acceleration, and that means the object is at rest. Alright, we're going to do some problems now. I would expect you guys to probably work these first, and then come back to the video and we'll work them together. Alright. A brakeman on a bobsled team slows the sled from 12 meters per second. So V I is 12 meters per second. To rest, okay, if he goes to rest, that means the final velocity, is 0 meters per second, because it says at rest. And it takes it over a time of 4.5 seconds. Calculate the acceleration of the bobsled. Well, acceleration equals Vf minus Vi over t. So Vf is 0. Vi is 12 over 4.5. 0 minus 12, of course, is negative 12. Negative 12 divided by 4.5 ends up being an acceleration rate of 2.7, and that would be meters per second squared, and it was a negative acceleration. Let me erase this and rewrite it down here. It equals 2.7, negative 2.7 meters per second squared. So there's our answer for the first one. Negative 2.7 meters per second squared. That makes sense because we would expect the acceleration to be a negative, since the velocity value apparently is traveling in a positive direction, since the 12 meters per second up here is positive. All right. Let's try the second one. A Vespa accelerates from 21 meters per second, so VI is 21 meters per second, to 27, so VF is 27 meters per second, with an average acceleration of 2.9 meters per second squared. Acceleration is 2.9 meters per second squared. The question wants to know, how long does it take this to happen? Well, it's definitely not 0. First thing we need to do is we need to look at our formula, which is acceleration equals VF minus, let's try this again. Alright, acceleration equals VF minus VI over T. So we want to solve for T. So we're going to multiply both sides by T to get rid of T on the bottom. And we have AT equals VF minus VI. And then we're going to get rid of A by dividing by A. So T is equal to what? VF minus VI over T. Oops, over A, sorry. Let me erase that. Over A. There we go. Alright. So we go back and look over here. What was VF? VF was 27. So 27 meters per second. Minus, what was VI? 21 meters per second. Over, what was the acceleration? 2.9 meters per second squared. So we have 27 minus 21. That gives us 6 divided by 2.9. T ends up being 2.1 seconds. So it took the Vespa 2.1 seconds to accelerate 6 meters per second. Alright, let's try the next one. Give some space over here for us. Alrighty. Gina's golf cart, Gina's golf cart accelerates at negative 1.4 meters per second squared from 7 So VI is 7 meters per second to a complete stop. So what would VF be if it's a complete stop? VF would have to be 0 meters per second. How long does it take the golf cart to stop? So we're finding T again, just like we did on the last one. And we solve for T up here, so we know T equals VF minus VI over A. So VF is 0, VI is 7, acceleration is going to be negative 1.4, so we have negative 7 over negative 1.4, and when we divide those out, we end up with 5 seconds. Notice how the time ended up being positive. You never can have a negative time. It's always going to be positive. And that makes sense because their acceleration was in a negative direction, and we would have expected the values to be negative to get the positive time. All right. Last one on this page. An aircraft accelerates from 10 meters per second, so from 10 meters per second, so that's VI, 10 meters per second, with an average acceleration of 16 meters per second squared for 12 seconds. T is 12 seconds. What is the aircraft's final velocity? All right, well, we're going to have to derive final velocity from our formula here. So, oops. All right, what's the first thing we need to do to isolate VF? Well, let's get rid of T. So we end up with AT equals VF minus VI. Now how do I isolate VF? Well, I add VI to both sides. That gets rid of VI over there, and then I add VI here. And so we end up with this derivation, VF equals AT plus VI. Alright, do we have everything we need over here? We have A, we have T, and we have VI. Perfect. So VF, alright, so we got VF is equal to A, which is 16, times T, which is 12, plus VI, which is 10. So 16 times 12 is 192 plus 10. 192 plus 10 gives us 202 meters per second for the last one on this problem. 202 meters per second. All right, during a takeoff, a Boeing 737 accelerates from rest. Well, from rest, again, that's going to be VI is 0. At 1.1 meters per second squared. For 0.9 minutes, anytime you have minutes given like this, it's probably a good idea to go ahead and convert them to seconds, since these up here are in seconds. You could keep it in minutes if you wanted, but let's go ahead and convert it. And when we do that, we get 54 seconds. And what do they want us to do? What is its final speed going to be? Well, we already derived for final speed on the previous problem. We know VF equals VI plus AT. So VI is 0. We pretty much can just ignore it. Plus A, which is 1.1, times T, which is 54 seconds. And 1.1 times 54 gives us positive 59.4. And we would want to put the formula for velocity, the unit meters per second. And there's our answer for the last problem. Now this last slide is a slide showing what we call kinematic equations. And these are basically equations that you won't have to memorize, but you will have to be able to use, and they are already, all four of them are already on your formula sheet. Some of them are derived from the acceleration formula, like this one here. Some of them are a combination of formulas between velocity and acceleration. But fortunately, you don't have to learn how to derive them. This one was kind of lost in translation. This VF should be up here, like that. And this should be here. So other than that, these are right. This should be V sub F. This should be V sub I. And this is AT squared. Again, these are on your formula sheet. So, and that'll be our next step after we feel comfortable with velocity and acceleration formulas. We'll start using these kinematic equations, which can be a little difficult, but as long as you take your time, write down all your knowns, so do a little sketch, you should be okay. All right.